Good afternoon. It's a matter of great to introduce Dr. Rudra N Sahoo. He did his PhD from IIT Ropar in 2009 with the topic role transfer in subbarrier. Those people who he did it from Utkal University in Dhenkanal College in 2011, and he finished his masters from School of Physics, Sambalpur University in 2013. Then he joined IIT Ropar for his PhD there last year, and currently he is joined as a postdoc in China Institute of Atomic Energy in Beijing, and he has calculations and measurements in subbarrier fusion. And today's topic is also on the topic as published recently: subbarrier fusion, interplay between nuclear structure and reaction delay. So before I let the mic to Rudra, I to be in the mute mode. If you have any question, you can hold your question till the end, and you can ask. And here you go.
Hello.
Hello.
Can I start?
Yes, yes.
Okay.
Start now.
I am very much thankful to the organizing committee Nuclear Theory Group, and I am also give thanks to the Dr. Chirajim Mondal for his kind words in introduction. And now I am starting my presentation. The title of my talk is Subbarrier Fusion, that is interplay between the nuclear structure and the reaction dynamics. Hope at the end of my talk you will understand how the nuclear structure and reaction plays an important role for the subbarrier fusion outcomes. And here I will start from the basic nuclear reaction, and I will end up with the ongoing problem in the subbarrier fusion. My talk is organized in the following way. First, I will give a brief introduction about the nuclear reactions and their classification. Then I will come to subbarrier fusion and the outstanding problems of this field. To understand these outstanding issues, we performed a few experiments at Inter-University Accelerator Center, taking 3537 chlorine plus 130 tellurium. There I will explain the detail about the experimental techniques and the result, and finally I will conclude my talk by explaining the ongoing research problem of this field and constraints in the theory and experiments. Nuclear reaction. It is a process where the mass, charge, and energy exchange between the projectile and target when two nuclei interact with each other, and sometimes a new element is formed. Generally, in the nuclear physics laboratory, we placed a thin foil as a target. You can see in this figure, thin foil as a target, and we bombarded the projectile from the accelerator towards the target. And after the interaction of the projectile and target, we are getting some particles. We are detecting some particles with detectors based on our physics motivation. And generally, the nuclear reactions are represented as A plus X equal to Y plus B. That is, A is our projectile, X is called target nuclei, and that is called A plus X is called incident channel, and Y plus B, that is Y our residual nuclei, B is ejectile particle. And there is an extra term, that is Q. Q is nothing but the mass difference between the incident channel and the exit channel. And Q is called the energy kinematics of the reaction. The Q value is depends upon Q is called the energy kinematics of the reaction. If Q is positive, that is called the exothermic reaction, that is energy emitted from a reaction. If Q is negative, energy is needed to initiate a nuclear reaction. According to the structure of the nucleus, nuclear reactions are classified as the compound nuclear reaction and direct reaction. And in direct reaction, the peripheral interaction takes place between the projectile and target. The direct reaction is mainly studied to understand the evolution of reaction dynamics from fixed inelastic collision to the quasi-inelastic collision. And these are further classified as the elastic scattering and transfer, where the transfer are further classified as the pickup reaction and stripping reaction. In pickup reaction, when a projectile comes towards the target, it takes some nucleons from the when the projectile comes towards the target, it takes some nucleons from the target. That is called pickup, and stripping is just its opposite process. And in charge exchange reaction, the proton is exchanged between the projectile and target. In the breakup fusion reaction, a part of the projectile fuse with the target, and next rest of the part is goes as a spectator in the outgoing channel. And compound nuclear reactions are the process where the projectile is completely fused with the target. And these compound nuclear reactions are studied to understand the static and dynamical properties of the nucleus. And these are further classified as the three types: fusion, fission. That is when we are providing much more energy as compared to the barrier. That is fusion. That means projectile completely fuses the target. Then due to it cannot sustain the input angular moment of energy, then suddenly divided into two parts. Barrier means since we are dealing with the two heavy ions, these heavy ions are highly positively charged. And when these two particles come towards each other, there will be a Coulomb repulsion. That is called the Coulomb barrier. And above barrier fusion, just when we are providing just above barrier, providing the project, giving the energy to the projectile just above the barrier, that is called above barrier. And sub barrier fusion, when we are providing less energy to the projectile as compared to barrier, that case also fusion gets happen. And why this happen, and this is an interesting process. I will mainly focus on this sub barrier fusion mechanism in this presentation, and this is a schematic representation of a different kind of nuclear reaction. If the head-on collision will occur between the projectile and target, the complete fusion process is more probable. However, if the interaction occurred in the peripheral manner, that means in the diffuseness region, the direct reaction probability get enhanced. Before going to the details of sub-barrier fusion, first I will explain the fusion mechanism, how fusion actually occurs. When a projectile comes slightly more energy as compared to the barrier, it completely fuses the target. And the projectile completely dissipates all its kinetic energy. After that, the repetitive interaction occurred between the internucleonic degrees of freedom of the projectile and target, and finally lead to a thermally equilibrated compound nucleus. Hello? Finally lead to a thermally equilibrated compound nucleus. And that thermally equilibrated compound nucleus comes to ground state by emitting particles like alpha, proton, and neutron. And when it has not much more energy to emit the particles, comes to ground state. In principle, by detecting any of the evaporation residue particle or the gamma ray, or directly detecting the evaporation residue, we can calculate the fusion cross section. And fusion cross section is nothing but a physical parameter which connects the experimental real world with the theoretical abstract world. I will explain it in the following slides. And I am interested in the subbarrier fusion because the subbarrier fusion mechanism explore the static and dynamical properties of the nucleus, provide a scope to go far from the nuclear stability belt. It also helps to create a heavy nuclei with longer lifetime, because in subbarrier fusion our excitation energy is less. And it also helps to understand the astrophysical process like energy production in stars, and it gives an idea about the internuclear potential landscape, that is not the barrier distribution of two interacting partners. And it has also probability to explore the new reaction dynamics at extremely below barrier. As per the existing literature and the present understanding, the subbarrier fusion occurs mainly due to the effect of tunneling. That is, tunneling is a quantum mechanical process. Tunneling is a quantum mechanical process where where a quantum mechanical particle pass through a barrier, although it has less energy as compared to that barrier. And the tunneling probability is get modified by the static deformation and the collective excitation and the PQNT channel, that is positive Q value neutron transport channel. And first I will come to the static deformation. You can see if the projectile and target both are in spherical, then the interaction distance, if there is a interaction distance between them is r. If we take a prolate or oblate projectile or target as for the reaction, then the interaction distance between them will be changed. And when the interaction distance is changed between the projectile and target, at that condition, the Coulomb barrier between the projectile and target also changed. Since the Coulomb barrier is inversely proportional to the interaction distance r. This is the experimental observation you can see for oxygen 16. This is the here three excitation functions are compared by normalizing energy with the corresponding barrier and cross section with the geometrical cross section, but here it is not showing on the y-axis. But here the cross sections are compared by normalizing the measured cross section with the geometrical cross section and energy with the respective barrier. You can see the samarium have the deformation, the samarium 44 and 148 and 154, the deformation parameter is gradually increasing. And when the subbarrier fusion cross section is measured, here is 1, that means ECM by BB is 1, means this is our below barrier data. And in the below barrier, the fusion excitation functions are diverging. However, in the above barrier, the fusion excitation functions are coinciding with each other. And with the deformation, with increasing in deformation, the fusion cross sections are actually increasing. That actually signifies that static deformation has some road towards the subbarrier fusion. Collective excitation. When projectile and targets comes towards each other, due to way of interaction as well as the stress between them, both nuclei get excited, and the rotational and vibrational state of the both nuclei evolved, and that's why this rotational and vibrational state of both the nuclei actually reduce the barrier. And you can see in this figure, that is the from AM Stefanini, you can see in this figure when 2 plus and 3 minus state of titanium and Fe56 is coupled with each other, then the barrier is reduced. Here you can see the dotted line represents the barrier due to one-dimensional barrier, only due to tunneling. However, when we are coupling 2 plus and 3 minus state, the barrier is distributing. Since here the barrier is slightly reducing, our fusion cross section is increasing in order of magnitude, because actually the Coulomb barrier reduce the fusion cross section exponentially when we will go down. That's why slight change in the barrier actually enhance the cross section in order of magnitude. And the static deformation and collective excitation are the obvious factor, because when two nuclei comes towards each other, these two factors comes automatically, because nuclei are the many body quantum mechanical particle. But there is some problem in the positive Q value neutron transfer channel. First, I will explain why positive Q value neutron transfer channel considered as a enhancing factor for the subbarrier fusion. You can see in this figure, schematic figure, this is the projectile, this is the target nuclei. When the projectile comes towards the target, before the interaction, neutrons try to actually transfer between the projectile and target, because neutrons are insensitive to the Coulomb barrier. However, when the neutrons try to transfer between the projectile and target, a bond is formed between the projectile and target nuclei. And when the bond is formed between the projectile and target nuclei, since the nuclear force is attractive in nature, sometimes the projectile gets trapped with the target nuclei. And after the projectile gets trapped with the target nuclei, due to the Q value is positive, the repetitive interaction occurs between the projectile and target. The internucleonic degrees freedom of projectile and target nuclei. That's why also that actually lead to a thermally equilibrated compound nucleus, and again it comes to the ground state with the general process. Due to this reason, the positive Q value neutron transfer channel is taken as a factor to enhance the subbarrier fusion cross section. Experimental observation you can see here, you can see calcium 40 and SN132 and calcium 48 plus SN132. In these cases, up to 5 neutron transfer channel having positive Q value. When one neutron transfer takes place between the projectile and target, the Q value is positive, and for 2 also, for 3 and up to the 5. But here we have the 5 positive, the 5 neutron transfer channel have negative Q value. That's why you can see in these cases, the fusion excitation function is actually enhancing when the Q value is positive. And in these cases, the fusion excitation function is reducing. And similar kind of observation you can see also in this case, calcium 40 and SN124. And here also, before comparison of the excitation function, the energy is normalized with the respective barrier, as well as the fusion cross section with the geometrical cross section, that is called reduced cross section. These are actually normalized to actually remove the barrier effect as well as the radius effect. This is the strong experimental evidence that P20 has some effect towards the subbarrier fusion. However, if we will see in this figure, here also we are here also six excitation functions are compared. Six excitation functions are compared by normalizing energy with the barrier and the fusion cross section, measured fusion cross section with the geometrical cross section. You can see in this 130 tellurium plus nickel 58 case, we have 11 positive equivalent neutron transfer channel, and in nickel tellurium 130 and nickel 64, we have only one positive equivalent neutron transfer. If you will see the excitation function, both excitation functions are falling one upon another, and coincide with each other, falling one upon another. That shows that P20 does not have any effect towards the subbarrier fusion. However, if you see in case of calcium and zirconium, and calcium zirconium 90 and zirconium 96, due to the difference in P20 channel, the excitation function is splitting. This effect, the effect of positive Q bar neutron transfer channel has some effects towards subbarrier fusion. It's first observed in nickel 64 plus nickel 64, this nickel nickel system. If you see in this system, we in the nickel 64 and nickel 64 and nickel 58 and nickel 58, we don't have any positive Q value neutron transfer channel. But in case of nickel 58 and nickel 64, you will get some two neutron transfer channel having positive Q value. That's why this nickel 64 and nickel 64 system and nickel 58 and nickel 58 system is following the same line. However, in this case, nickel 58 and nickel 64, the fusion cross section is enhancing as compared to these two systems. And this kind of observation you can also get from nickel 64 and germanium 74 and nickel 58 plus germanium 74. And one more problem in the subbarrier fusion is that the coupled channel calculation, the theoretical calculation of coupled channel will predict the fusion excitation function at below barrier. And if we will go to extremely below barrier, below 600% below barrier, the fusion excitation function, the measured fusion excitation function is either enhanced, either actually hindered from the theoretical prediction, and sometimes it get enhanced. Then this region is not known to us. It will go down to the 6-7% below barrier. If I will summarize the problems in the subbarrier fusion, in the field of subbarrier fusion, the effect of positive Q value neutron transfer channel is not known to us, whether this has some effect towards subbarrier fusion or not. If really the positive Q value neutron transfer channel is effective towards the subbarrier fusion, then up to how many neutron transfer channels are really effective? This is also a question. This is also not known to us. And the third question is that the behavior of fusion excitation function at extremely below barrier. The behavior is not known to us. To understand these problems, we actually performed few experiments at Inter-University Accelerator Center, taking 35-37 fluorine as the projectile and 130 tellurium as the target. And we chose these two systems because these two systems are differ by 6 neutron transfer channel having positive Q value. You can see in 35 fluorine case plus 35 fluorine case, you will get up to 6 neutron transfer channel having positive Q value. However, in case of 37 fluorine case, you will not get any Q value, the neutron transfer channel having positive Q value. And if we measure the fusion cross section of both the systems and we compare, then we can easily conclude whether P20 is effective towards the subbarrier fusion or not. And for that, actually, this is our experimental setup, and the target 130 tellurium target we prepare at the target laboratory of the Inter-University Accelerator Center, and we prepared using the resistive evaporation technique. First, we prepared the 130 tellurium target. Try to prepare self-supporting 130 tellurium target, but we could not able to prepare. Although we take few attempts to prepare. After that, we prepare this 130 tellurium target on the carbon backing. And 35-37 fluorine beam is taken from the 15 UD pilot at IUSC. And this is our beam direction. This total is our experimental setup. You can see this is the beam direction and this is our target chamber. Target chamber plays a crucial role to perform the experiment. Here you can see this was the target chamber setting for my experiment. You can see this is the beam direction and this is the target holder. And when this target holder is movable during the experiment, we can place the target based on our convenience. That's why it is movable in nature. This target. Here we fixed two target, two tellurium target, 130 tellurium with carbon backing and one quartz crystal. This quartz crystal is fixed here to focus the beam properly. And when after focusing the beam, actually we replace the quartz crystal with a different target to perform the experiment. And also when the beam is falls on the target, after that whether the beam is falling properly or not on the target, we actually fix two monitor detector to monitor the beam, incoming beam. If we get the nearly equal number of elastic scattering in both the monitor detector, that is nothing but surface silicon barrier detector. The rule is it only count the number of number of elastic scattering particles. If we will get nearly equal number of particles both the monitor detector, then we will say that the beam is falling perpendicularly and we perform our experiments. And after performing, when the projectiles collides with the target nuclear, there are so many nuclear reactions occurred, and in outgoing channel we will get different kind of particle. And this is the actually very good setup that actually transfer the desired particle, which particle we want, desired particle from target chamber to this focal plane without losing its energy. This is a very good setup. And in the focal plane, we are placing a multi-wire proportional counter, that is a gas detector, to and measure the energy of the desired particle. But in our cases, the desired particle as the evaporation residue. We are calculating the fusion cross section by measuring direct the evaporation residue. And the total length of the Vira is equal to 8.5 meter. If we actually measure the distance, it is from target chamber to focal plane. Total length is the 8.5 meter. And this is Q1, Q2 is the quadrupole. This quadrupoles and Q3, Q4 also quadrupole. These quadrupoles are responsible to focus and defocus the beam. And electric dipole actually separate the particles according to their energy by Q ratio. Q is charge state, and magnetic dipole separate the particles according to their momentum by Q ratio. And again ED2 separate the particles according to their E by Q ratio. And this ED, MT, and ED fixed in such a way that it separate the particle according to their mass by Q ratio, M by Q ratio. And by identifying their M by Q ratio, we can measure the evaporation residue. And you can see this is the real setup of the evaporation. This is the real setup of the heavy ion reaction analyzer. Here this is Q1, Q2. This is the incoming beam direction. Here there is our target chamber. Here is our Q3, Q4. And this is electric dipole ED1, and inside this there is a magnetic dipole, and this is ED2. And now question is that how we will measure the evaporation residue? Although we will transfer from target chamber to the focal plane, how we will measure the evaporation residue? Since after the reaction from the kinematics, we can calculate the recoil energy of the evaporation residue by using this formula. For our case, the evaporation residue energy equal to 25 MeV. If we calculate the energy of the evaporation residue, then we can calculate the time of flight of the evaporation residue. And the time of flight of the evaporation residue from target chamber to the focal plane, it will take 1 microsecond. And we can calculate the charge state using this formula. And from the kinematics, we can calculate recoil energy, time of flight, and the charge state. Accordingly, we provide the electric and magnetic field to the electric dipole and magnetic dipole and quadrupole. And after that, what happens? Sometimes, although we are calculated from the theoretical calculation this value, but sometimes we are not getting the particles in the focal plane properly. That's why we actually take the slightly change the recoil energy and charge state, and we try to maximize the count state in the focal plane. When we look at the maximum number of count state at a particular energy, that is taken as a granted that actually in this case this is the good setup. And this setup actually has the work to transport the particle from target chamber to the focal plane without losing its energy. And we have the timing information as well as the energy loss information. If we make a gate properly by taking timing information and energy loss, we will get this kind of spectra. You can see here. These are the tight gates. In this, you can see these are the tight gates. This is the energy loss of the evaporation residue. This is the timing difference. That is timing information. You can see I am showing here three spectra for this 37 chlorine plus 130 tellurium. and with decreasing here, this spectra is just above the barrier. This is 7% below barrier, and this is at 10% below barrier. And when we are actually going from above to below barrier, the evaporation residue count rate is gradually exponentially decreasing. And you can see at 10% below barrier, we are only actually getting the 8 evaporation residue. And this is a question whether these 8s are evaporation residue or these are from the elastic scattering particles comes to this gate. To confirm these 8 particles are the evaporation residue, whether these are actually evaporation residue or not, we actually removed during the experiment. We removed our target from the beam line, and we only projected the beam inside the Hebbian reaction analyzer, that extended setup. And we didn't get any count within this gate, and that signifies that these 8 particles are the evaporation residue. And similarly, for 35 chlorine case and 130 tellurium case, we also measure the evaporation residue at a different energy, and I am showing only here 4 spectra. So far, so good. We measure the evaporation residue of the both system at different energy, from 15% below, 15% above barrier to 10% below barrier. And cross section is the cross section correlated between the experimental real one and the theoretical abstract one. I earlier I also told this, and this is the actually formula to calculate the fusion cross section experimental. This formula we can actually derive from the fundamental principle of the cross section calculation. And here this is the fusion cross section, and this is our efficiency. Efficiency, what is efficiency? It, since we are transferring the evaporation residue from the target chamber to the focal plane, we are not transferring all the evaporation residue. If 100 numbers of evaporation residues are producing the target chamber, we are only transporting 10 to 11 evaporation residue in the focal plane. That's why this factor is taken into account. And YER is our number of evaporation residue, YM is our geometrical monotorial, and this is the Rutherford calculation. And YM is the count, YM is the solid angle sustained by the monitor detector with the target. And using this formula, we can calculate the fusion cross section. You can see for this is for 35 chlorine case, and this is for 37 chlorine case. We calculate the fusion cross section for 35 chlorine case. You can see from 0.03 milliband to the 650 milliband. And in this case also 1 microband to 650 milliband. And here we measure the fusion cross section up to 6 order of magnitude. And you will not get this kind of experiment in any other field of physics except the nuclear physics. This is the beauty of nuclear physics. So far so good. We measure the fusion excitation function of both the system. Now our motive is that we will see whether our case the neutron transport channel has effected towards superheat fusion or not. For that, to understand this, we actually normalize the energy with the respective barrier and measure fusion cross section with the geometrical cross section. And when we compare both the system, you can see at above barrier fusion, the fusion excitation function is coinciding. But in the below barrier, the fusion excitation function is diverging. That strongly signifies that in our case, in this system, the positive Q value neutron transport channel has some effects towards the subbarrier fusion. And this is the experimental observation we observe, but we don't know, since we have 6 positive Q value neutron transport channel in case in the 35 chlorine cases, but we don't know which neutron transport channel is how much effective, because we didn't measure the transfer cross section. And that's why again we also did the theoretical calculation using the coupled channel calculation. And this coupled channel calculation has the capacity, it can calculate the cross section using one-dimensional barrier penetration model. We can implement the inelastic excitation inside the code, and we also couple the two neutron transport channel if some cases it is needed. In case of 37 chlorine case, as we know, we don't have any neutron transport channel having positive Q value. That's why we first try to match our experimental data with theoretical prediction, and it is well matched with the theoretical prediction when we add the rotational and vibrational state of this both the system, vegetarian target. However, if you come to this 35 chlorine case in this system, up to 6.7%, 6.5% below the barrier, the coupled channel calculation reproduces the fusion excitation function, but below barrier it is not reproducing the fusion excitation function. That's why we actually add the two neutron transport channel, the cross section of two neutron transport channel. Then when we are adding the two neutron transport cross section, the fusion excitation function is well reproduced by the this coupled channel calculation. From this calculation, we experimentally as well as theoretically confirmed that the couple channel, that positive Q value neutron transfer channel has some effect toward the subarray fusion. Since in case of 37 chlorine case, we measured the fusion excitation function down to 1 microton per section. We also did the barrier distribution calculation. You can see this is our one-dimensional barrier penetration model. This barrier due to one-dimensional barrier penetration model. And when we are, this is the experimental barrier distribution. And the barrier is here actually drastically changing. That's why cross section are enhancing in order of magnitude. As earlier I told that the fusion excitation function, the behavior of fusion excitation function at extremely below barrier is not known to us. That's why we did the S factor calculation. You can see with the decreasing in the energy, S factor is gradually increasing. There is no gradually increasing. We have not seen any dip here. That's why it is very difficult to say whether, although it is clear that there is no fusion hindrance, again to confirm clearly whether fusion hindrance is there or not, we also did the S factor calculation by taking the derivative of S factor, and this is nothing but the slope of the S factor. And we didn't get any fusion. With decreasing energy, our LE factor also increasing gradually, and we didn't see any down curve. That's why there is no fusion hindrance up to 1 microbarn per section for 37 chlorine case. Maybe if we will measure the fusion excitation function down to that, then we will get the fusion hindrance. But up to 1 microbarn per section, we didn't get any fusion hindrance. And since we measure the fusion excitation function of the both the system in the 37 chlorine plus 130 tellurium and 35 chlorine plus 130 tellurium, we compared our measured fusion excitation function with the other measured excitation function. You can see in this 37 chlorine cases, we went down to 4 order of magnitude, went down to the 3 order of magnitude as compared to the earlier measurement. And in this 35 chlorine case, we actually went down to 1 order of magnitude as compared to the earlier measurement. If you will see in these cases, all the excitation functions are following the same line after normalizing the energy with the barrier and the measured fusion excitation function with the geometrical cross-section. In case of 35 chlorine and the magnesium case, you will get magnesium case, the fusion excitation function is actually enhancing. You can see here, this is the experimental observation. And that signifies that not only the neutron transfer channel having positive Q value enhance the subarray fusion, but the reaction Q value also plays an important role to enhance the subarray fusion, enhance the fusion cross section at below barrier. And summary of this experiment is that we measured the fusion excitation function of the 35-37 chlorine with 130 tellurium from 10% below barrier to the 15% above barrier. And 35 chlorine plus 130 tellurium system excitation function is significantly enhanced as compared to the 37 chlorine plus 130 tellurium system. The effect of positive equivalent neutron transfer channel has been observed and emphasized from the coupled channel calculation. And we didn't get any fusion hindrance for this 35 and 130 tellurium system up to 10% below the barrier. And so far, then I will come to theoretical and experimental challenges. So far, the message is that from this study, the message is that the subbarrier fusion is subbarrier fusion is occurred due to the quantum mechanical tunneling, and the tunneling probability is influenced due to the static and dynamical deformation of the projectile target. And positive Q value neutron transfer channel also has effects toward the subbarrier fusion. I am not actually since in the most of the experimental observation, the positive Q value neutron transfer channel enhance the subbarrier fusion. I am from my experience and the knowledge, I would say that positive Q value neutron transfer channel has some effects toward the subbarrier fusion. And this is the message and of the subbarrier fusion study. Due to this reason, the subbarrier fusion is going to happen. And the experimental method, what is the problem in the experiment? That is, it is very difficult. The problems in experiment is that it is very difficult to get a pair of system to study the positive Q value neutron transfer channel effect. And the system I told you, that is 35-37 chlorine plus 130 tellurium. These are the very rare. You will get very rare if you will search this kind of system, and this is very difficult to search a system. Although if you will search a system to study the positive Q value neutron transfer channel effect, at the below barrier, it is very difficult to calculate the very difficult to actually measure the cross section, because the elastic scattering probabilities get enhanced. That's why when we are transferring the evaporation residue from the target sample to the focal plane, it is very difficult, because the elastic like particle also go inside the zigzag motion and interrupt with the evaporation residue. And since one more thing is that if you will go down to the below barrier, then the evaporation residue energy also decrease. Since if the evaporation residue energy will be decreased, kinetic energy of the evaporation residue will be decreased, then we cannot transfer the particle from the target chamber to the focal plane. And there is also other method. We can measuring the characteristics gamma ray from the evaporation residue. We can also measure the fusion cross section. But if we measure the actually the characteristics gamma rays, since the other kind of reaction also occurs at the same times, then when we will get 6 or 7 gamma rays at a particular from the evaporation residue, that actually diminishing by the other kind of reaction particles and the other kind of reaction, gamma rays from the other kind of reaction. Then these are the actually experimental these are the experimental problems. This we have to clarify how we have to go down much down to the below barrier. And in theoretical model, there are many theoretical model which already given by many people. That is proportional calculation, quantum proportional calculation, empirical proportional calculation, fusion function model, Olsky energy model, and Jagrevey semi-classical model. These are the models actually prepared to explain the excitation function of fusion excitation function at extremely below barrier. But here, no one is the universal model, that no one model is explained all the excitation functions so far measured. And so far measured, each model actually explain the fusion excitation function of few few systems of some mass region. That's why if we understand all these existing theoretical models and compress a good model, maybe we will come up with a good solution to explain the fusion excitation function properly, the experimental future excitation function. If we slightly extrapolate the problems in the subbarrier fusion, then the questions are the following: the individual contribution of the each neutron transport chain, the individual contribution of each individual factor is not yet explored. The meaning of this that we know that the subbarrier fusion is happening due to the static deformation, the dynamical deformation, or and the positive Q value. Then which factor is how much responsible? This is not known to us. And the result of excitation function, the behavior of excitation function at extremely below barrier is not known to us. And the quantitative contribution of each neutron transport channel. Since in our system, what I showed you, we have 6 neutron transport channel in 35 chlorine gases, but we only know that the neutron transport channel has some effect towards the subbarrier fusion, but we don't know the quantitative contribution of each neutron transport channel. And one more thing is that in our system, I told you up to computational calculation reports the fusion excitation function down to 6.5% below the barrier. Then question is that from which neutron transport from which how much percent below barrier the positive Q value neutron transport channel actually operate to enhance the fusion cross section. This is also not known to us. And one more interesting problem I will say here, since I always telling that the neutron transport channel and the positive Q value neutron transport channel, if you come to the transfer side, when the transfer reaction is occurring, you can see the transfer reactions are actually occurring in the successive manner. You can see in this spectra, as well as you can see in this spectrum also the transfer reactions are occurring in the sequential manner. And you can in these are the 4 reference I am showing here, where you will get that the neutron are transferring from the successive manner. However, if you will see this reference from the Kalkali scale I am showing one figure, here the 3 neutron and 4 neutron transfer probabilities are same, and there is also experimental observation, and 1 and 2 neutron transfer channel probability are nearly equal to same. Then actually we don't have any clear understanding about the neutron transfer, how the neutron transfer takes place from the projectile to target or target to projectile. Then these are the problems in the neutron transfer, the mechanism transfer mechanism, as well as the subbarrier fusion. And these are so many problems to understand and to tackle all this problem. We have to go along we have to work properly, and we have if we collaborate with theoretical people and experimental people, then we can tackle some of the problem, and we have a long way to go to explore the this kind of problems. And thank you.
Thank you very much, Rudra, for the beautiful talk. So the session is
Welcome.
now. So the session is now welcome for questions. If anybody has any questions.
Um, Hello, I'm Tatagata. I have a question. Rudra.
Okay, yes.
The static deformation for both the nucleus, 35 chlorine and 37 chlorine,
Yes.
uh, were, are same or not?
No, the both differences are not same. One case for 35 chloric acid it is 0.24, and for 37
Mhm.
case it is 0.11.
That means and 0.24 you said, right?
Yes.
For 35,
Yes,
and for 35 you are getting enhancement
yes,
at
yes, yes,
sub-big air.
yes.
Okay, that means as I think you have seen that in actinide region also there are
Okay.
so many papers that due to static deformation sub-barrier fusion enhancement occurs.
Uh-huh.
So that, as you have currently correctly pointed out, that can
Yes.
also be one
And
reason. So
and
for for this six. Positive Q value neutron transfer channel solely is it happening, or there is some part of that deformation is playing a
Okay,
role?
that is a very good question. I also don't know actually. If we'll see also 35 and 37 chlorine case, if we'll see the
Mhm.
valence shell of the 35 case, the valence shell of neutron is half filled, and in 37 chlorine cases, the valence shell of the neutron is full filled. Actually, we didn't measure the neutron transfer cross section of these two systems. If we will measure the neutron transfer cross section of these systems and we add in the our calculation, then we can easily say whether what is actually going on. But we don't have any we don't have any solid reason for that. For that, we have to measure
Mm.
the transfer reaction cross section.
Okay. And
And
and that astrophysical S factor you said that is also not decreasing with decreasing energy,
yes,
right?
yes.
If it was decreasing, then
We
you
will
could
confirm
get
that there is some fusion hindrance or something. And also L factor is not decreasing. You will see the L factor is also not decreasing. That is also going increasing with decreasing energy. That
which
signifies that
factor?
up
L.
to L factor.
Okay. Hmm.
Eh,
Okay. Thank you.
that
Hmm.
Okay. Any other questions, comments?
Excuse me, sir.
yes.
Sir, will you please tell me the difference between static deformation and dynamic deformation?
Okay, and the static deformation is the intrinsic property. That static deformation is the deformation when the nucleus is in the stable condition. You will get that in static deformation. And dynamic is that where both nuclei comes towards each other. Since nuclei are quantum many body system, that actually the different states are evolved. And when different states are evolved, we will get the dynamical deformation. That original deformation will change.
Hello,
Yes,
Rudra sir, I have a question. Can I
yes,
ask?
yes.
Actually, have you checked the Q value for charge particle like proton or something? Because in that case, you have to check the optimum Q value also in this case. So, have you checked for?
Actually, before the experiment, I was actually calculated all the Q value of neutron transfer stripping pickup. All this I have calculated. But since this was the ongoing recent ongoing problem, and that actually And I have not actually calculated any optimum Q value, but optimum Q value also a factor you can check into
Yes.
it. But I have not included here.
Okay, because for like charge particle like proton transfer or pickup on or stripping, in that
Uh-huh.
case, if we check that matching condition, if the Q optimum is matching with the Q value of that reaction, then there may be a possibility of that charge particle transfer.
Actually, this is the comment I got from also one referee that why we are not taking the proton transfer channel, right? And I reply to this referee that since neutron is insensitive to the Coulomb barrier, this is more
Yes.
probable as compared to the proton. That's why you are including the neutron transfer channel, not the proton. Proton may have effect, I don't know, but neutron is more efficient to explain the subbarrel fusion because it is insensitive and make a bond between the projectile and target. But proton has not that much of capacity to do, right?
Yes, 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 but we have not measured the transfer probability in this case.
Uh,
So,
actually, actually, you know the situation that beam time, right?
yes,
As you are experimentalist, you will not. Although you have a plan to measure, but you will not get the beam time. It is very difficult to get the beam time. But you had a plan to measure this transfer.
yes, yes, yes. Okay, okay. Thank you.
Okay, okay.
Sir, what is the coupling strength for your different kind of reactions?
Coupling strength means the transfer coupling strength, right?
Yes, sir. Yes, sir.
Actually, we are here. Actually, if you see the literature, people are taking zero point 0.2 everywhere. But our cases also it is 0.2. 0.2 is matching. But since we don't know the transfer reaction, we didn't measure the transfer cross section. It is just to match the theoretical experimental cross section with the theoretical calculation. But there is you cannot say it is 0.2 or 0.3, right? When we will measure the fusion cross section, the transfer cross section for the both the system, at that time we can also calculate this transfer strength. What is the strength? Now we cannot say. It is just only match the experimental data with the theoretical calculation.
Okay,
I
sir.
have another question. Uh, Hello,
Yes, yes, yes,
Rudra. We all know that CC full only can take up to two neutron transfer.
yes, 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 yes.
So, have you any plan to try Fresco where you can have more flexibility
This
to?
is very good question. Tathagat bhai, if you help, I will also try. But I don't know the fresco. That's actually very difficult to learn. Actually, I have tried. I installed in my computer. But
Uh,
if you will not get any input, then it is very difficult to learn. If you will help me, then I will be ready to work. I will
no,
ready to
no.
work and yes.
I have also not worked with Fresco and
Fresco.
all, but Delhi University people may know. I don't know right now who is there.
Recently here Professor Pillai is here and he is guiding to the Mallika, one of my junior.
Hmm.
She is actually using the Fresco with some transfer calculation with the light beam. I am trying to learn from her, but let's see.
Hmm.
What is the due to the corona situation whether I will stay here or not go. But if I will stay here 1 or 2 months, then I will do this. This is my next plan.
Hmm.
This is my next plan. Thank
Yeah,
you.
that would be good because nowadays, na this CC full started means came in 1999,
Yes,
and
yes.
then many paper came
Yes,
using
yes, yes,
CC
yes.
full and all.
Yes, yes, yes,
But
yes.
nowadays, it is like everything can be reproduced with CC full. So,
Yes, yes,
like,
that is correct.
yeah,
That is correct. I also told this. To publish the paper and to match our experimental data with this
yeah.
calculation. And
Okay, okay,
okay,
fine. Thank you, thank you.
Sir,
yes,
so you said that by transferring of neutron, in that case, if it has positive value,
yes,
no effect you can see on the fusion cross section within transfer
okay,
of each neutron. Then
okay.
how you can compare with its value or not? Matlab, how you can say that it can change or not?
If I understood correctly, that your question is that how neutron transfer, how I am emphasizing that neutron transfer is enhancing the cross section, right?
No, sir. My
Oh,
question is only is that if you can calculate the positive Q value,
okay,
then
okay.
you can say that fusion cross section change.
Yes.
right? But
Yes.
you said in your presentation that within changing the neutron or by transferring the neutron one by one, fusion cross section is not changed at each step. Then why?
No, no, no. I am not telling this. I told that I got the signature that the neutron transfer channel has some effects towards the submarine fusion. I don't know which neutron transfer channel is how much responsible towards the submarine fusion. We also don't know. Unless and until we cannot measure the transfer channel, we cannot say, right?
Okay, sir. Yes, sir. Thank you, sir.
Yes. Okay. Okay.
Any other questions, comments? If not, then I have some primitive ones.
Okay.
So
Yes.
this may not be so technical because I don't understand all the intricacies of your
Okay. Okay.
experiment. Can you
Yes.
please go to slide number 9, please?
Yes.
9, yes. So I see the red line and the black line in the right hand side.
This one, right?
Yes, this one
Okay.
where your cursor is right now.
Yes.
Yes.
Yes. Yes. Yes.
This is a plot in the log scale in the y-axis.
Yes. Yes. A log scale.
So if I take the absolute value,
Okay.
I think if my eyes are telling me right things, the
Okay.
ratio of the reactions are almost same throughout the
Yeah, yes, that is a
whole
very
energy range.
yes, I got your question. Actually, this is very interesting. If we take this the linear scale, then you will see the fusion excitation function at above barrier. Since in the below barrier, our cross section are order of microbarn or microbarn and very less.
Mm-hmm.
And order of magnitude, you can see it is 10 to the power minus 5 nearly equal to, and it is 10 to the power minus 4. This is at 2 energy point. Our processions are increasing in order of magnitude,
Mm-hmm.
microbarn to millibarn. That's why
Yeah.
we are actually to show this difference. We are taking the logarithmic scale, right? Yes, if
Yes.
you yes.
Yes. So the thing is that because you said that below the barrier you have this I mean this difference growing up between
It,
35 chlorine and 37 chlorine.
yes, yes, yes,
But if I go by the absolute value, then
yes.
is the ratio is almost same throughout the whole energy range.
You cannot see, but in the linear scale, the cross section are that means it will start from zero, right?
Yeah.
You cannot go to down. If you go down, then you cannot differentiate between the very the below zero. It is very difficult to differentiate. That's why we are taking the logarithmic scale to differentiate both the excitation function at the below barrier.
And in the next slide, in the next slide, slide number 10. Can you go to slide number 10, please?
So 10, it is 10.
No, yeah, this is 10. So here also I see the theoretical line
Yes, yes, yes.
in the right hand side, kind of
This one.
crossing at the right hand, this one, yeah.
Yes, yes, yes.
It's kind of crossing the experimental line and then staying a little bit below.
Yes, 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 yes.
Uh, is this the
Huh.
reason what Tathagata was telling about the CC4 limitation of?
Yes, yes. This is the actually the questions people are asked related to this, because you can see here we are actually taking the transfer factor 0.2, transfer factor 0.3, and all these things, and we are matching with the experimental data. But in principle, if we measure the transfer cross section of each neutron transfer channel for both the
Hmm.
system, then we
Hmm.
can easily say what is the this neutron transfer factor, and we can easily say how up to how much percent below barrier, below which percent below barrier the neutron transfer are actually effective towards the submarine fusion. And it is the theoretical calculation is done only to represent that the PQ and T, positive P value neutron transfer channel, has effect to show this. But this is not the strong evidence that the for our experimental observation. But this is only to show.
Okay. Okay. And during your
I
talk,
think
yeah.
mm, mm, I think Chiru has rightly pointed out two things. Hmm. I'm very happy to hear that. This Rudra,
Yes.
in your CC pool calculation, you used wood section parameterization,
Yes,
right?
yes, 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 yes.
And okay, and have you tuned those diffuseness parameter
Yes,
uh,
first,
zero
actually, I tuned the
zero
parameter. How I will tune actually? How I tuned? First, I will check the calculation theory from the potential parameter from the pulsation potential. Then I first match in the above barrier. When it is matched in the above barrier, I take this as a granted and did the CC calculation.
but mm, but when you matched in above barrier, in that
Yes.
case, in the CC output, what barrier value is it is showing?
That is
Does
actually
does
coming.
that
That is
match with actual barrier?
That actually not perfectly matching. In our case, this is 104. That means 103 or something or 3 point something. It is common about to match.
Because because this theory people, Chiru, Bhumika, they all know that this diffuseness parameter, if you slightly change, na,
And then
uh,
that is actually
can yeah, it can in your sub-barrier region it can enhance more, or
I
in
will
the
show you. I will show you the proof.
above
You can
barrier.
see
So
in this.
yeah,
Tathagat bhai, you can see in this figure
uh,
the barrier distribution, the one dimensional barrier penetration. First I matched, right? You can see
mm,
the nearly equal to 104, right? As you
I'm not talking about one-dimensional barrier penetration because that is just for reference. That is
but for taking one
not
dimensional
sure that
barrier.
is started one-dimensional because
No, no. Actually, from one
people
dimensional barrier penetration model, you have to tune the parameter na, by taking one dimensional barrier penetration model. Then
because
you have to go to the couple channel
yeah,
calculation.
yeah, yes,
That's
yes,
why
yes.
I first tuned, and you can see the barrier is here, and you can see also barrier 104 or something like,
Yeah,
right?
that's why I told that better to mention in the presentation that I have used this wood section parameterization, and I have used this diffuseness parameter, R0
Hmm.
parameter, and V0 parameter. Because if you people change those, people manually make shallow potential or deep potential and reproduce cross section
Then
excitation
if
function.
we do this, na, there is no meaning of this calculation. If we change the barrier, if we change
Ah,
the barrier, automatically fusion procession will be reproduced in the below barrier. Then what is the meaning of this, right?
no, 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 not barrier changing. I am talking about that V0 potential.
Okay, 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 okay.
So, so that in that wood section parameters I am talking.
Okay.
So better to say those parameters that I have used these.
Okay, 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 okay. That I have to mention. Okay, okay. Thank you.
Uh,
Mm,
I will
Tathagata
mention.
sir, I think that crossing in the theoretical calculation may be due to the shallow potential. In slide number
yeah,
10.
that's what I was actually afraid of.
Yeah, yeah, because in they are crossing each other at a particular energy. In this case,
Uh,
yeah, large figure in third figure, yes.
yeah. This CC full, na, it is sometimes very much confusing because
Yes.
parameters actually um, playing major role, very much confusing. That's why my suggestion would be use some other model also to verify.
Yes, yes. That the year the fresco will be better, right? I have to work on it, but
Oh, that I don't know. That I don't know actually. I have not worked in that region.
yeah.
Yeah.
But I have heard that people use Fresco, so maybe I suggest.
I also know people are using, but I
Huh.
have not seen any significant calculation using the fresco. But in India now, people are working on it, transfer and fusion and all this, backup fusion.
Okay, nice presentation, Rudra.
Okay,
Good luck.
thank you, thank you.
I have a more academic concern about this 9 and 10 slide
Okay, okay, okay.
because in the lower energy region I can see there are some error bars, but I
Yes,
don't
yes.
see them in the higher energy points.
Okay, that actually inside the error bar. Okay, if we I am not showing here the linear scale calculation. If
Ah,
I
okay,
show
okay.
to the linear scale, you will see visible on the error
They
bar. But
they
since
got
it is
diminished because of the log scale. Okay, okay,
yeah, log scale, right? And
okay,
yeah, that is inside the point.
okay,
Okay.
okay. Thank you, Rudra. It was a very nice talk.
Okay, thank you, thank you so
Uh,
much.
thank you, Rudra bhai. It's really
Okay,
interesting.
thank you. Yes,
I think,
Yeah,
yeah, there is a question.
yeah.
Hello.
Yes,
yes.
go ahead.
Okay, so I have one question regarding the angular momentum conservation. When you have that transfer reaction, how you deal actually? I just want to know a little bit. You are
Om Mrutyunjay bhai, okay, okay, okay. You tell. Actually, I didn't do any transfer calculation here. Actually,
okay.
okay. Only I have calculated the fusion cross section.
Okay. In case of your fusion here,
Okay.
so you deal all possible angular momentum, or your calculation in L equal to zero system like that.
Actually, in CC full calculation, all the actually there is a angular distribution in the CC full calculation. If we the
What
theoretical
is that,
calculation,
sir?
I
Yes.
did.
That's
I did, but I am not showing here. I actually for up to how much linear orbital angular momentum don't know, but we did this. I
okay.
actually I forgot. I can see the calculation again up to
Oh,
how
that
much it
means
is.
okay. I mean, more clearly, like it, that all possible angular momentum you have taken, or just like you have to manually taken
No, no,
using
all.
base.
I have taken all. I have taken all.
Okay.
Not change anything there.
And how to deal the recoil energy or in the CC pool, or you neglect that part.
No, no, no. I actually in the we are not recoil energy we are providing when we are calculating the actually efficiency. At that time we are providing to the core task.
Okay.
But recoil energy we are calculating for the this kinematics to transfer the particle to provide the electric and magnetic field. In the recoil energy and charge state we are calculating to provide the electric field and magnetic field to the different elements such that the desired particle, our case is the evaporation residue will transfer from target chamber to the focal plane. That's why we are doing. But the calculation is different.
Okay, a beautiful talk you have. After a long
Okay.
time, I talk to you.
Yes. Thank you so much. I also after a long time.
Okay,
Okay.
yes.
Okay.
Okay, so any other questions, comments?
Wonderful talk, Ruth.
Thank
Really
you. Thank you so much.
see.
So that means we close the session. Thank you again, Rudra.
Okay. Thank you, Stinuda.
Yeah, you have
And all
a
the
wonderful.
I will thankful to all the organizing committee of this nuclear theory group for giving this chance. Thank you so much.
Thank you so much.
Bye bye.
Bye bye.